Alright, this asks us to use summation formulas with the limit as n approaches infinity to evaluate the area under the curve represented by the integral from -2 to 3 of x cubed plus 1 dx. And just so we can get an idea of what this curve looks like, here's one of our previous graphs that we were looking at. And before we were doing Riemann sums using left endpoints and right endpoints, and then we did one of the same function using midpoints. And we weren't taking the limit as n approaches infinity, we were just capping it at 5 subintervals, if you recall. But if we were to take the limit as n approaches infinity, we would have a closer and closer approximation to the area underneath this curve. Underneath the curve from on the interval that we care about here from -2 to 3. So we could do that one of a few ways. We could use right Riemann sums, we could use left Riemann sums, but I find it's a little bit easier just to use right Riemann sums and then just to take the limit as n approaches infinity. It just seems to make it a little bit cleaner. So let's just pattern match here with our formula and see if we can come up with the notation that we need to work with here. So this is telling us that the integral from a to b, in this case -2 to 3, of some function, in this case our function is x cubed plus 1, is going to equal the limit as n approaches infinity of the summation from 1 to n of f of x sub I multiplied by our delta x, or our change in x. Here our change in x is defined by b minus a over n. So our b minus a in this case is going to be 3 minus 2, or 3 plus 2. That's going to give us 5. So this is going to equal, let's see, our a is equal to -2. Our b is equal to 3. So our delta x is going to equal 5 over n. Now remember, we don't know what n could be. It's going to be infinitely small as n approaches infinity. This change in x here is going to be infinitely small. Next up we have our x sub I, which is defined as a plus some increment of our subinterval here. So this is going to be a, which is -2. I should put it like this: x sub I is equal to -2 plus some increment of our change in x. Well, we defined our change in x as 5 divided by n, and as n approaches infinity, this is just going to become smaller and smaller. So 5 over n. And this represents our x sub I. Now, our function of x sub I is going to equal x sub I cubed plus 1. So that's going to be, I'll try to make room here, -2 plus I times 5 over n, all of that cubed, plus 1. Alright. So that means that we're going to be taking the limit. We're going to be taking the limit as n approaches infinity of the summation from I equals 1 to n of f of x sub I, and that's going to be, the whole thing is going to be multiplied by our delta x here, so I'll put it in brackets here. Negative 2 plus I times 5 over n, all of that cubed, plus 1, put into brackets, multiplied by our change in x, which is 5 over n once more. And this is the summation that we're going to be evaluating as n approaches infinity. So I'm probably going to need to start with another sheet here to give us plenty of room. I'll go to the bottom of this one here. Well, what we can do is we can expand this. So this is going to equal, well, for starters, we have a negative 2 here out front, so why don't we put the negative 2 on the other side? That won't really change our expression. Limit as n approaches infinity of, try to write a little smaller to save some room here, I equals 1 to n brackets of I times 5 over n, that's going to be minus 2 there, cubed, plus 1, close the brackets, multiply everything by 5 over n. Alright, now we can expand this. And I'm just going to expand the cubed expression here. This is equal to the limit as n approaches infinity of, why don't we bring our 5 over n out front, and then we can put it back in later. We can do that because it's just considered some constant. I equals 1 to infinity. And I'm just going to expand what's in here. That is going to give us I 5 over n cubed plus 3 times, I'm just using Pascal's triangle here, I 5 over n squared times negative 2 plus another 3 times I 5 over n times negative 2 squared minus, let's see, when we have this negative 2 cubed, that's going to be negative 8, and then plus 1 is going to give us minus 7. And then we can clean this up a little bit. This is going to equal the limit as n approaches infinity. We'll keep our 5 over n out front here for the moment. The sum from I equals 1 to n of, keep our brackets, and this is going to be I cubed, and then we'll just distribute our cubed here. This is going to be 5 cubed is 125 over n cubed minus we're just multiplying by the negative 2 here, so that's going to be minus 5 squared times 3 is going to give us 75, times 2 is going to be 150, so that's going to be minus 150. And we have our n squared under here in the denominator. Don't forget your I squared there. Plus, and I know I should have probably kept the I squared on the same side like I did the I cubed over here, but we'll just ignore that for the moment. Plus, negative 2 squared is just going to be positive 4 times 5 times 3 is going to give us 60. All of that over n. We just have a single n there in the denominator. And don't forget we're multiplying by I here. And then we still have our minus 7. Alright. So just bring this up a little bit. Now what we can do is we can distribute our sigma function here, our sigma notation, to each one of these expressions, and then whatever constants that we have, including the n terms, we can just pull them out front of the notation there. So make sure that you can see well here. And this is going to equal the limit as n approaches infinity. Always make sure to write your limit every time so that we can remind ourselves what we're working with. This is one of the mistakes of beginning calculus students, is that sometimes you might forget to write the limit, and then halfway through the problem you might forget what your goal is or what you're working with. Here we have 5 over n, and we'll just keep our brackets. This 125 over n cubed here, we're going to pull that out because it's just going to be, we're just going to treat it like a constant. And then we are left with the I cubed on the inside of the sum. Everything's going to be from I equals n to n. I cubed. And then we have another constant that we're going to pull out as we distribute our summations. 150 over n squared. The sum from I equals 1 to n of I squared. And we're going to pull out another constant, plus 60. Plus 60 over n times the sum from I equals 1 to n of just I. It's supposed to be an I. Minus, we're going to pull this constant out, and we'll just say that we have the sum from I equals 1 to n of just 1. This is a 1 here and not an I. And then we'll close our brackets. Well, now we know how to evaluate this, because if you remember our summation formulas, well then we can just plug those in here for and evaluate for n. So let's do that. This is just going to equal the limit as n approaches infinity. We're going to keep our 5n out front here. We have 125 over n cubed. And now this this I cubed expression is just going to get evaluated as n plus 1 over 2, all of that squared. And if this seems like a little bit of magic, I invite you to go back and review your summation formulas for I cubed, I squared, and I, and so on. And this is going to be minus 150 over n squared times, we're going to evaluate the sum of I squared from 1 to n is just going to equal n times n plus 1 times 2n plus 1, all of that over 6. And we could simplify this here, but I'll leave it for now. And this is going to be multiplied by, added to 60 over n and we're going to evaluate here for I. The summation of I is just going to give us n times n plus 1 over 2. And then over here at the end, and then we're kind of running out of room on this side, but this is just going to be minus. If you remember, the sum of from 1 to n of 1 is just going to equal n. So this is just going to be minus 7n here. Minus 7n, and then we'll close our brackets. Alright, so this can be simplified a little bit here. When you distribute this squared here, you're going to get an n squared here. And because you have an n cubed in the denominator over here, n cubed, two of these powers are going to cancel out with your n squared up here. So let's say if you distribute your squared here, that's going to be n squared, and that whole thing is going to cancel out with 2 of these, leaving just n to the 1. So I'll just cancel that out, and we'll just leave the n here and know that it's an n to the 1. Similarly, you have an n here that's going to cancel out with one of these n squared exponents here, leaving just n here in the denominator. And here you have a 6, here you have a 150. So why don't we cancel that out, and we can just say that we have a 25 up here. And if any point you need to stop and just work out the algebra for yourself just to verify everything, I encourage you to do that. You will learn more that way when you're exercising your brain. Don't just take my word for it. This n's going to cancel out with that n. This 2 is going to cancel out, leaving just 30 up here. There we go. And now we can expand some of this. This equals the limit. I'll try to bring it over to the left a little bit more so we don't run out of room again. As n approaches infinity of... Okay, now we'll distribute, let's distribute our 5 over n here. So when we distribute our 5 over n here, we get 625. We get 625 over n squared. Now I'm going to expand this n plus 1 over 2 squared and we will get n squared plus 2n plus 1, all of that over 4. Here we have a minus. Let's bring down that minus. And when we distribute our 5 over n here, we are going to get 25 times 5 is going to equal 125. N times n is going to equal n squared. And when I FOIL this out, that's going to give me 2n squared plus 3n plus 1. 5 over n times 30 is just going to give me 150 over n. And that's going to be multiplied times our n plus 1 here. And finally, 5 over n times 7n is just going to leave us with, the n's are going to cancel out, that's just going to leave us with a minus 35. Now, this requires a little bit of thought here. I want you to think about what happens as the limit as n approaches infinity. What happens as the limit of n approaches infinity? Well, we're going to have some n squared term down here in our denominators, or an n term over here. That's just going to get multiplied by this, and there are some n squared terms here that are going to cancel out with the denominator, and then there's some n terms, or just some constant terms here that will not cancel out, and as n approaches infinity, they will just go to 0. So we can jump ahead, or think ahead, and think about what terms are essential here to our evaluation. What terms are not going to go to 0 as n approaches infinity? And that's what we're going to do in our next step here. So let's do a little bit of algebra here. This is going to equal the limit as n approaches infinity of, let's say we have 625. I'm just going to swap the 4 and the n squared around here. You'll see why here in a moment. And I'm going to distribute this n squared in our denominator to each of these terms here. So here we have an n squared. This is going to be a 2n and 1 over n squared. Each of them is going to be over n squared. Now notice, this term is just going to go to 0, and this is just going to go to 0, and this is going to go to 1. So as the limit of n approaches infinity, that's like saying that we have 625 over 4 times 1, which is just going to be equal to this. Now, when we have our minus 125, and I'm going to do the same thing here. I'm just going to distribute the n squared term in the denominator that we had among these things here inside. N squared plus 3n plus 1. Here we have the over n squared over n squared over n squared.